This video is a direct follow-up to the previous video. In this video, we're going to continue looking at the structure of GL2 mod SL2. In the last video, we discovered that the left cosets for this quotient group, which would look like B times SL2, that's nothing more than the set of matrices inside GL2 such that the determinant of that matrix is equal to the same thing as the determinant of the coset representative. In other words, determinant of A and determinant of B are the same thing. We also have some notation that I want to establish. If I let the matrix ER be the matrix R001, where R is inside of the non-zero real numbers, then it turns out that the set of matrices in GL2 that have determinant equal to R can all be thought of as belonging to the left coset ER times SL2. We might also want to write that as R001 times SL2. And so the other thing that it's worth remembering from the previous video is that A times SL2 will equal ER times SL2 if and only if the determinant of A winds up being the determinant of ER, which is R. In that last video, we also introduced but did not have a chance to explore a function. So we're going to define a function f that goes from GL2 mod SL2 into the non-zero real numbers, and we're going to define this by f of any left coset is just the determinant of the representative of the coset. And the claim is that f is a group isomorphism. Now, to show that this is a group isomorphism, there are several things that we need to do. The first one is, because cosets have multiple names, we do need to show that f is well-defined. In other words, we need to make sure that the value of f does not depend upon the name that we choose for a particular left coset. The second thing is that we're going to need to show that f is one-to-one. The third thing that we're going to need to show is that we're going to need to show that f is onto. And then the fourth thing that we're going to need to show is that we will have to show that f preserves the group operation. So we're going to look at each one of these things. Let's see, I need to make that more readable. So we want to show that it preserves the group operation. And we're going to look at each one of these questions individually. So the first question, is f well defined? Well, what that means is, if I happen to know that this particular left coset and this particular left coset are one and the same, then is f applied to this coset equal to f applied to this coset? Well, the main thing that we have to remember is that we've already seen in the previous video that these two guys, these two left cosets, are equal if and only if A inverse B belongs to SL2, and that happens if and only if the determinant of A and the determinant of B are exactly the same. So yeah, what that means is that f of this particular left coset name will be the determinant of A. F of this coset name is the determinant of B. But by this fact right up here, we know that these two things are indeed equal to each other, and therefore we can indeed say that if the two left cosets are equal, then f gives me the same answer, regardless of which name I use. In other words, f of A times SL2 is equal to f of B times SL2. And so that says f is well defined. We do indeed have a function. Well, what about one-to-one? Now, the thing here is we have to be thinking in terms of what if the answers are the same? So we are going to be looking at if f sends this particular left coset to some number and f sends this left coset to the same number, is, well, I should say are, the two inputs equal to each other. Because if I take two different inputs, here's an input and here's an input, and I get the same output, if that implies that in reality I actually had the same input, then the function is one-to-one. So this is how I go about showing that f is one-to-one. Well, what we're going to notice is that this particular hypothesis here is going to give us a little bit of extra tools that'll help us figure out what we need to know. So the first thing that I want to notice is that f of A times SL2 equal R says for sure that the determinant of A is equal to R by the definition of f. And f of B times SL2 is equal to R says for sure the determinant of B is equal to R by the definition of f, because f sends a left coset to the determinant of its representative. In other words, f of A SL2 is going to be the determinant of A, and f of B times SL2 is the determinant of B. And so if we've set them both equal to R, that gives us these two equations. So we now know that the determinant of A is equal to R, and that's equal to the determinant of B. So what that says is that we also know something else. We know that the determinant of A inverse is 1 over R, because the determinant of any inverse is always 1 over the determinant of the matrix. And this then says that we know that the determinant of A inverse times B is equal to 1 over R times R, which is 1. So A inverse times B does indeed belong to SL2, and that's enough to say that this left coset and this left coset are equal as sets. And hence, F is 1-to-1 as needed. So we've now got F is a 1-to-1 function from the quotient group to the non-zero real numbers. So our third question is F onto? Now, to figure out whether or not F is onto, what we have to do is we have to pick an arbitrary element of the non-zero real numbers. So we have to say for any r inside of the non-zero real numbers, can we find a left coset, so and A times SL2, ooh, that's kind of weird looking notation, A times SL2 inside the quotient group such that F of that particular element is indeed equal to little r. Well, this one is very easy. Given little r inside of r star, we can look at the matrix that we were calling ER earlier, which is R001, and that guy is in GL2 because the determinant of ER is R times 1 minus 0, which is R. And so we can look at this guy and note that F of ER times SL2, that particular left coset's just going to be the determinant of ER, and the determinant of ER is certainly R, and so that lets me conclude F is onto R star. So we now have a function that is 1-to-1 and onto from the quotient group to the non-zero real numbers. We will have a group isomorphism if this particular function preserves the group operation. So let's now look at the group operation. Does our F preserve the group operation? Now, what this question means is the following. We're going to ask, is F of ASL2 times with BSL2 the same thing as F of ASL2 times F of BSL2? Now, it's important to note that this particular operation is in the quotient group, whereas this times is in plain old real arithmetic. So that's the question that we're going to be asking ourselves. Well, we need to set up a little bit of notation. So we're going to let the determinant of A be some real number R1 inside of R star. So I do know that R1 is not 0. And we're going to let the determinant of B be some real number R2 inside of R star. So R2 is also known not to be 0. And we know that we can do this. We know that we have these two facts because we are assuming that A and B are in GL2. So we know those two things. because we are going to squish up here that let A and B be two arbitrary elements of GL2. And so the determinant of A and the determinant of B are known to not be 0. Now I'm simply going to compute each side. F of A times SL2 O times with B times SL2 is going to be F of AB SL2, and this is by the definition of coset multiplication. In other words, by O times. But I know what F does. F sends a left coset to the determinant of the representative. So the definition of F says that F of that left coset is the determinant of A times B. And that's by the definition of F itself. And the determinant of A times B is going to be the determinant of A times the determinant of B. That's by our big theorem from an earlier video. And so we have this is indeed equal to R1 times R2 inside of the non-zero real numbers under their multiplication. Well, we can keep going. And this next step is going to kind of look silly, but it's just that I wanted to stress that that really is a multiplication of two real numbers. But let's keep going. What we've got here is that R1, remember, is indeed the determinant of A, and R2 is the determinant of B, and it's just worth pointing out that this star is in the group R star under times, and the determinant of A is nothing more than F of A times SL2, and the determinant of B is F times B, F of B times SL2. And so what we now have is that if I take the start, which was F of this coset multiplication, I now have real multiplication of the images of the two cosets. In other words, what we have indeed established is F of this coset multiplication is going to be F of the first coset times F of the second coset. And it's worth pointing out that this particular operation is in GL2 mod SL2, and this particular times is in R star under ordinary old multiplication. Technically, I should say this is in that group. And then the final thing that I want to point out in understanding this isomorphism stuff is that this is do the operation in the domain group first, and then do F. But on the other side of this particular equal sign, we have do the function first, so that we now have elements in R star. Then we do ordinary old multiplication inside of R star. In other words, to really understand the structure of this group, what we want to be thinking about is a diagram that we can think of as running around in two different ways and we get the same answer. So what I want to do is I want to be thinking about this kind of a diagram. We can think about starting out inside of GL2 mod SL2. So we have two things in that particular group. And we can compose them. And then we can take that element by F to get F of A times SL2 O times with B times SL2. Or what we can do is we can take each one of these elements individually and use F on them to get the determinant of A. Well, actually, I want to write it in function notation, so let's to get F of the first coset and F of the second coset. And these guys are inside, this side is in the non-zero reals under multiplication. This is under O times. And then we can multiply these two things together. And this answer, when we multiply them together, is going to be the same as that answer. So we get the same regardless of whether or not we do the group operation first. Group operation first, followed by function, or whether or not we do the function first, followed by the group operation in the second thing. And so what this actually means is that structurally, GL2 mod SL2 under its coset multiplication is just like R star under its multiplication. So everything that we know about R star under its ordinary old multiplication applies to the quotient group GL2 mod SL2. In particular, so everything we know about this particular group applies to this particular group. So in particular, one of the most important things is we do know that R star under multiplication is commutative. Hence, we know that the quotient group GL2 mod SL2 is commutative, even though neither GL2 nor SL2 is. And that's a really important idea, that sometimes a quotient group of two non-abelian groups can be abelian. And that will be enough for this particular video.